All right, welcome everyone. So in this video, we are going to try and diagonalize a 3 by 3 matrix A, where in this case, it's an upper triangular matrix. Notice the first column is 2, 0, 0. The second column is 4, 2, 0. The third column is 6, 2, 1. So we have all of the entries below the main diagonal are all 0. So this is an upper triangular matrix. So step 1 in this process is find the eigenvalues of the matrix. And again, because this is triangular, we know that the eigenvalues of this matrix are going to be the diagonal entries. So that means we have one eigenvalue, which is 4, and we have a second eigenvalue, which is 2, and that eigenvalue has multiplicity 2. And for each of these eigenvalues, step 2 in the process was to go ahead and find eigenvectors for each eigenvalue, and hopefully we have enough linearly independent eigenvectors to construct a matrix P that's going to diagonalize this matrix. So looking at the eigenvalue 4, we could go ahead and set up this equation that we want to solve, which is when is the A minus lambda I times x going to equal the 0 vector. And so we take A minus lambda I, where in this case our lambda is 4. So we're subtracting 4 from each of the diagonal entries. So that gives us -2, -2, and 0. And the off-diagonal entries have not changed. So I still have zeros below the main diagonal, and I've got my 4, 6, and 2 above the main diagonal. So now I want to know when is this matrix times x equal 0. And so there should be at least some non-trivial solutions because 4 is an eigenvalue. And I will leave the linear algebra work for finding a solution set here to you, but you can verify that the solution set to this equation, we have one free variable, x3, so we can write solutions to this equation in the form some scalar x3 times the vector 5, 1, 1. So therefore, I know the vector 5, 1, 1 is a basis for the eigenspace for the eigenvalue lambda equals 4. So now I've got one eigenvector so far, and lambda equals 2. This has multiplicity 2. So we're hoping from this eigenvalue, we can identify 2 more eigenvectors. So again, we're going to want to solve the same equation, which is when is A minus lambda I times x equal to the 0 vector. So in this case, our lambda is 2. So we subtract 2 from these diagonal entries, and that gives us 0, 0, 2 along the main diagonal. And all of the entries above the main diagonal and below the main diagonal, they don't change when I subtract lambda I from matrix A. And so from this coefficient matrix, we can express this in reduced row echelon form, where we have column 1 does not have a pivot, so x1 is free. From column 2, x2 does, there's a pivot in this column, so this tells me that x2 would have to equal 0. There's a pivot in column 3, so this tells me x3 has to equal 0. So now we can see what the solutions are going to look like to A minus 2I times x equals the 0 vector. Namely, we have one free variable x1 times a vector of the form 1, 0, 0. So all of these solutions, x2 and x3, have to be 0, and x1 can be anything that it wants. So a basis for this eigenspace is the vector 1, 0, 0. So now we've only added one more eigenvector. Any other eigenvector that this matrix has is either going to be a scalar multiple of the eigenvector 1, 0, 0, or a scalar multiple of the eigenvector 5, 1, 1. So we do not have 3 linearly independent eigenvectors. So therefore, A is not diagonalizable.